show you the solutions. So I've done most of the correcting, but not all of it. But this problem seems to go generally, most people got the idea. So we have an algorithm where T of n is recurrence, and the actual complexity is n. And so we want to draw a recurrence tree for 3 levels. So this is 1, 2, 3 levels. And so therefore, at level 0, we have the actual work being done at n. And then we split n over 3 and then n over 5. And then the work being done is going to be, when n over 3 goes in, the work is going to be n over 3. And then n over 5 goes in, the work is going to be n over 5. So if you add across here, it basically, you can put this over 15. It gives you 8 n over 15, or 8/15 n. If you do it for the bottom level, again, you're taking the third, and the third is a 9. The third of a fifth is a 15. A fifth of a third is a 15. A fifth is a 25th. So we end up having this situation here. When we add all that together, we get, well, we get 64 over 225. But we are looking for a pattern here, and the pattern was 8/15, and actually 64 is a squared, and 225 is just 15 squared. So we generalize to see that we're going to have 8/15s to the first power times n, 8/15s to the 0 power, the first power, etc. Like that. So that's kind of what I was looking for. Any questions? So I want you to solve this complexity for this tree using a geometric series. That's a big clue. You should be getting a geometric series. That was a clue, and that's a geometric series. So basically we have 8/15s to the 0, 8/15 to the 1, 8/15 to the 2, 8/15s. Now we know that this tree is not going to have the same depth everywhere. We know that the right side of the tree will be the what? Shortest, the smallest height, and this part will have the longest height. So the tree will kind of generally have this shape like this, so it's going to be kind of like this, and it's going to kind of go like that. It's going to be kind of jagged. So it's unfair or incorrect to say that every level is going to have the same, just take this 8/15 to the greater power. By the way, what is this exponent? This exponent corresponds to the what? To the depth. So depth is 0, 1, 2, 3. So because the tree will become a little bit jagged here. It'll kind of look like this towards the bottom. But we can still solve for the complexity by recognizing the fact that we're adding this, plus this, plus this, plus this, so many times, all times n. So what we have here is basically 1, which is to the 0, 8/15s, 8/15s squared, 8/15s cubed, and then we're going to do it some number of times. That's called k times. So that's why I use k here. Now you can say, well, we don't know what k is. K is really not a real number because this thing is not going to have the nice, true, full shape. Right, but because we have a geometric series and the ratio of the geometric series is less than 1, we know that even if we go to infinity with k, this series is going to converge. So what we're going to do is basically add this up and assume k is a very large number. Well, how about infinity? It's a pretty large number, so it's not a number, but okay. So as k goes to infinity, if this tree were to go on to infinity, doing what it's doing here, the sum of these coefficients will add up to the geometric series as k goes to infinity. And you can see that if I take the limit as k goes to infinity of the geometric series, which is a minus a times r to the number of terms, 1 minus r, as k goes to infinity, this is a less than 1, this just goes to 0. So the only thing remaining here is going to be 1 over 1 minus 8/15s. Well, 1 minus 8/15 is 7/15s. 1 over 7/15s is 15/7. You still have this n. So it tells us that if this tree was going to go to infinity, infinite number of depths, forever, then the amount of work being done altogether would be 15/7 n. Which means if this tree would be to go to infinity in terms of height, we would have a linear amount of work. Is that correct? But if we look at this tree over here, we see that how much work is being done on level 0? Linear. So could this tree do any less than linear work?
No.
Could it do any more than linear work?
Yes.
No. It can't, because even when I push the number of the depth to infinity, I still get linear. It's still only a constant times n. So we are stuck. We have a lower bound of n, which is linear because of this level. But when we kept adding these together, when we added these together, we basically still get just a constant times this n. So therefore, this algorithm will do no less work than n because it's doing n at level 0. But even if you push this tree to a ridiculous infinity, it still will do a linear amount of work. So therefore, we have can't do any less than n. Look at the level 0, and can't do any more than n. Look at it when I push it to infinity, which is impossible. So it cannot. So actually, it will still do n, but the constant in reality will be smaller number than that. So 15/7 is the absolute upper bound of the total amount of work being done in the tree if this tree would just go on without stopping, using the same less than 1 ratio. So therefore, that's a very interesting observation. So therefore, I say clearly state if the answer to B is big O, big theta, or big omega. Well, first of all, since it can't be any less than n, and it can't be any more than n, then it is proportional to n. So therefore, saying it's theta n is the correct answer. Now the question is, could it also be big O of n and big omega of n? And the answer is yes, because those allow for proportionality. If I use little o or little omega, then the answer would be no, because big O means that it's actually less than n. And it's not. It's really proportional to n. So how many people think they got very close to it? Most people are very close to it. Very close. I think so. Both people did very well. Okay. All right, so that's fine. So therefore, now I don't put the reasons here, but I just told you the reason verbally. I'm looking clearly states. I'm looking for some words here. I'm looking for some thinking. I know it's a lot to ask, but I'm looking for some thinking. Okay. So the next problems, I think are pretty straightforward, hopefully. So we found that f of n is n squared log n. Oh, you know something? I just realized I made a mistake in the grading room. Because I thought I had n squared log squared n. Okay, so I think most of these I took points off. Once you turn back on. Okay. So we have n squared log n is the actual complexity. And then n to the log b of a is n to the log 3 of 9. But n to the log 3 of 9 is n squared. Okay? So we have n squared here, we have n squared here. So therefore we have a situation where f of n is equal to n to the log b of a times lg to some k exponent of n. And that k value is equal to? 1. So k is equal to 1. So when we have that, this is case number what? For master algorithm. Case 2. So therefore we're going to say n squared log n is equal to n squared log first power n. Therefore our complexity should be n squared log lg second power n. And I think most of you get that also. Which is good. Any questions? For some reason, I thought there was a second power here, so I was expecting to get a 3 here, but it wasn't a 3, it was a 2. 2 is correct. Now, I think one person got a 3, I don't know what I got. But most people got a 2. I think one person got a first power. At least you get the idea, right? All right, so the next one, basically, we have T of n is 3 times T of n over 4 plus square root of n, so f of n is n to the half power. So n to the log b of a is n to the log 4 of 3. Now, I don't know if you had a calculator on you, but most of you had a calculator. But even if you don't have a calculator, what is log 4 of 3? I don't know, but it's the power you raise 4 to make 3. 4 to the first power is 4. It's too high, so it has to be less than 1. The actual number ends up being about 0.79. You can get that on a calculator. And log to the base 4 of 3 can be rewritten as the natural log of 3 over change base. How do you change the base from log 4 to natural log? Log base 4 of 3 is equal to natural log of 3 over the natural log of 4, which is 0.79 approximately. So you can see that this number, 0.79 and 0.5, is asymptotically higher. Right? So therefore this is 0.5, this is 0.79. Therefore our complexity is n to the n, theta of n to the 0.79. Some of you left it as n to the power of log 4 of 3. I assume you did it on the calculator. And I counted that correct. If you did a calculator, you at least recognize the fact that this is probably going to be more than 0.5 and certainly less than 1. And it's a correct answer. And except that you have to know that log base 4 of 3 is more than 0.5. That's the only thing you have to know. And how can you test that it is? How can you be sure? How can you be sure?
Log base 4 and 4 is root 4.
If you take 4, if you take the square root of 4, you'll get 2. And it's not enough. So you know it's going to have to be more than that. Okay. So if it was 0.5, then the square root of that would be. All right, so that's that. Any questions on that? Okay, good. All right, so the next question, this was where the fun begins, right? I think this question was too much fun. I think it was maybe too much fun for me to make it up. And you're like, that's not so much fun. That question had a bunch of things to think about, so let's think about them right now, kind of figure it out. So we want to use an approach from the class to determine the number of shapes that a tertiary tree can take on a given height of h. So graphically find solutions for 0, 1, and 2, and then generalize your answer for h. And draw a full tertiary tree of 3 down here. Okay. So for 0, it means that there are going to be 0 nodes in the tree. So that's a 0. So therefore, the only shape we have is an empty root pointer. That's one shape, so the answer is 1. That's a circle. If we have one node, the only node we're going to be able to have is a root. So here's a root, and that only can have one shape. So far it's just the same as a binary tree. When we get to 2, things get more complicated because it's a tertiary tree. So the number of shapes, you have to have a height of 2. So you have to have a root, and then you have to have something at the next level. So you can have a left child, a middle child, or a right child. But you could have 2 children also at that level. So therefore, how many ways can you have 2 children? Well, you can have left and middle, left and right, or middle and right. So this is all the ways we can have 1 child. This is all the ways we can have 2 children. And this is all the way, which is all the way that we can have 3 children. And that's a total sum of 1, 2, 3, 4, 5, 6, 7. So the goal was to basically, if you can draw this graphically, to come up with the first 3 numbers, which is going to be 1, 1, and 7. And of course, now here I'm showing you how to go to 3. If you're going to have 3 nodes, you're going to have a root. And then you're going to have a left subtree. Actually, hold on a minute, that's wrong now. I'm thinking myself. hold on a second, I'm gonna change, this is the wrong answer, so it's a good thing I didn't grade that yet. That's because I forgot the middle. Never mind, okay, so we're gonna skip this question. We're gonna skip this question, hopefully it's not too hard, okay. All right, go to the last question. Yeah, I thought I had the perfect answer, I knew it took me too short a time, okay. So I have to have 3 subtrees, possible subtrees. Which means, yes,
The C and D bits in that property?
huh?
The C and D bits in that question?
C and D?
Yeah.
Not sure what you're saying.
Questions. Sub-questions? C and D?
Oh, we can go through that.
Yeah.
I think we can go through that, as long as it doesn't base itself on this. Okay, so assume that every non-leaf node has 2 key values. Okay, so if you're looking, so for example, if that's the case, if a non-key node, non-leaf node, so that would be this one, this one, this one, and this one, right? And then all of these would have how many values? Assume that every non-leaf node has 2 key values. For such a non-leaf node, each left subtree has keys that are less than the, no. Okay, then assume that the leaves have only a single key value. So how many keys are in this tree? 15? 17, is it 17 or 15? So 2, 4, 6, 8, and then 9, so 17. Does that make sense? So determine the number of full keys in a tertiary tree of height 4. This is wrong too. That's a height 3. What's wrong with me? Okay, so, okay. I don't know what's wrong. Okay, so let's figure this out the correct way. So that would be very easy to do, because basically what you would have is you would have how many nodes here? 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 times 3 is 27. So we've got to remember the 27, and then we're going to have 1, 2, 3, 4, 5, 6, no. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. That's right? 9, 10, 13, right? 13. 13 times 2, 26 plus 53. So 53 should be. How many people got 53? Okay, you did better than me. All right, good job. All right. Okay, so that should be 53. Anybody got 17? Okay, that should be 53. Consider a full tertiary tree with height equal to 2. Determine the number of insertion sequences which can produce it. I believe my answer is correct. How many people got 12? Anybody got 12? Okay, so how do we do that? Well, basically, you have a full tertiary tree. Well, if you make the assumptions from C, if the height is 2, how many keys are going to be in this whole tree? Because you're going to have a root, and it's full, so you're going to have a left child, middle child, and right child. If you count 2 keys here, and 1, 1, 1, total 5. So let's assume that there are going to be 5 keys, and the keys are going to be specifically 1, 2, 3, 4, and 5. Then we know that the root has to have which values in it? It has to have a 2 and a 4. The root has to have a 2 and a 4. The reason for that is because if the 2 and a 4 go into the root, then there will be 1 left child, less than the smallest. There will be 1 right child, more than the biggest, and there will be 1 child in between the 2 keys. Okay? So, we have to get 2 and 4 as the first 2 entries into the tree. Because if you put 2 and 3 in, then 2 and 3 are going to go into the root. And then there'll be nothing between them, so you won't have any middle children, you won't have a full tree. So you can start, since you need 2 and 4 as the first 2 keys, you can start with 2, or you can start with 4. If you start with 2, you must follow it by 4. Once you have the 2 and the 4 in, then you have the remaining numbers 1, 3, 5. It doesn't matter which order they go into. So you have 1, 3, 5, but it could be 1, 3, 5, it could be 3, 1, 5, 5, 1, 3, 3, 5, 1. How many different permutations of 3 numbers are there? There's going to be 3 factorial or 6. So basically 2, 4, followed by 6 finishes. So 2, 4 followed by any of the 6 permutations of 3 is going to give us 6. If you start with 4, then you must immediately follow by 2. And then again, you're still left with 1, 3, and 5, and those again can be in 3 different permutations, which is 6. So therefore, these 6 permutations starting with 2, 4, and these 6 permutations starting with 4, 2 add up to 12. Now find the probability that a random sequence of keys, 5 keys, produces a full tertiary key. Okay, so find the probability that a random sequence of 5 keys produces a full tertiary tree. Well, we know there are 12 of them. Probability has to be, is basically the number of ones that produce a full tree over all the possible permutations. Well, how many permutations of 5 numbers do we have? That's going to be 5 factorial. So therefore, the probability of random sequence producing a full tree is going to be these 12 over all the possible permutations of 5, which is 120, which gives us 1 over 10, or 10%. How many people got that? Not too many, okay?
Oh, I screwed up part D.
Don't panic. I mean, I'm just saying this part D or E. So, but even if you got this a little bit off, but you got that right, you can still get a lot of credit. I'm not gonna take it, oh, you missed this one, so the whole question's off. I had to take a lot of credit for my own question, because I messed up. So the bottom line is, each test I grade, I look into what you've done in the previous parts, if they're gonna be based on other parts. So if there's something you screw up in one part, but then you did something correct in the other part, you still did reasonable thinking. That's really the bottom line here. Okay, is there any more? Is that it? That's it for that one, right? Okay, so let's go, now we go to the last question. Last question was very easy, too easy, right? It was so easy, people were shocked. What's so easy? It's too easy. Okay, so the question was, consider the average complexity of 2 algorithms, A1, A2. P is the probability value, given this T1, T2 of n. Find the algebraic value for P for the condition T1 less than T2. Well, T1 is less than T2, that means that this is less than this. So we have the left side less than the right side. And then what we're going to do is just multiply it out. So I have P and Q plus, now we have n squared minus P n squared less than n cubed. What is this one? Yeah, n cubed minus P n cubed plus P n squared. Then I put everything with a P on the left side. So I had this on the left side and this on the left side, and I combine that. So I have P n cubed minus P n cubed, so that became 2 P n cubed on the right side, on the left side. I had minus P n squared, and I had another, was it a minus or a plus?
So minus P n squared on the left and a positive P n squared on the right.
No, what's it?
So
Okay, I'm sorry, I'm all over the place there, okay. So it's minus P n squared and a positive, so we're gonna subtract, so we're gonna get minus 2 P n squared. So make sure I don't mess up anymore, okay. So we have 2 P n cubed minus 2 P n squared less than whatever's remaining here, which is gonna be n cubed, and then take this on the other side, minus n squared. So then we can factor out what we have, which is 2 P n squared in each of them. 2 P n squared times n minus 1 is less than n squared, factoring n squared, times n minus 1. Dividing by n squared, now be careful when you divide by n squared, it's an inequality. Are we dividing by a negative value? And the answer is?
no.
Because n is a large positive value, so squared is going to be positive. It's negative, it's n squared, but it's not. So dividing by a positive value does not change the inequality. And that gives us, after dividing by 2 times n minus 1, P is less than n minus 1 over 2 times n minus 1. These two are factors that can cancel once into each other. We have P is less than 1/2. So that's the value. So find the algebraic value of P. So algebraic value of P is 1/2 times n to the 0. And it disappears from the problem, right? So therefore, what are the values of P when n is equal to 10, 100,000? And it's going to be all the same. How many people got a bunch of 1/2s? Okay. That's just the way it worked out. So basically it means it doesn't matter how big the problem is. If the probability, whatever the probability represents, is less than 1/2, algorithm 1 is better. Now, when are the algorithms the same?
P is equal to 1/2.
When P is equal to 1/2. And when is the other one better?
P is greater than 1/2.
Yeah, that's it. Those are the options. Okay, find the value of P for very large values of n. Still 1/2. How many people got still 1/2? Okay, that was a, I guess the question was so easy that it was too easy, and people thought we have to make it more difficult.
For me, it was the, find the algebraic value. I assumed that there should have been n left.
But if you look at this, see, this is, people, a lot of times, and I don't blame you, because you guys are the ones taking the test. But if you look at this question, and if P is equal to 1/2, notice that we have half of an n cubed, and we have half of an n cubed, and half of an n squared, and half of an n squared. So you can see visually, so if you didn't trust your solution, put that value P back in and say, what the heck is going on here? Well, what's going on here when P is equal to 1/2, those are exactly the same. When P starts getting bigger, what happens to this? The cube term becomes heavier, right, than the quadratic term. So if P is equal to, like, for example, more than 0.5, then the cubic term here will be less than 0.5. And this is more than 0.5, this will be less than 0.5, which means that this will be more than 0.5. So, that's the way that one worked out. All right, any questions? All right. Don't worry about your grades. Everybody will probably do just fine. I didn't see any really bad papers so far. Of course, I didn't look at problem 3 yet.
I have a question for the question 1.
Yes.
About the depth, the K. I think the K is also, like, we should consider about the N, because, like, the K should be like log N, so we cannot ignore this K. Doesn't
I
it?
understand what you're saying.
Yeah.
The reason it doesn't matter is because, as I mentioned, the tree will be shortest here and longest here. So it will kind of look like this, right? If you were to draw the whole tree for any particular number. So what we did was basically say, okay, let's continue this infinitely and see what happens. And what happened was that the sum of the work converged to a constant times n. So now this is not, so this result, 15 over 7n, we will never see 15 over 7n work. But as n becomes larger and larger and larger and larger and larger, it will approach 15 over 7n. It's an absolute upper. So we found that the upper bound was linear, and we saw that the level 0 is linear. So you can't go any higher than upper bound, and you can't go any lower than level 0, because you're doing it. So therefore, the whole work was. Now, this was the easier version of the problem. Another version I considered giving you was the same thing, except instead of n, this was n squared. It is more complicated. The reason it's more complicated is because what goes here now? N squared. And when we get here 1/3, and this becomes what? 1/9 n squared, and this becomes 1/25 n squared. And then when you go to the next level, this is becoming n over 3, n over 3. So this is going to be 1/81 n squared, right? This is going to be 1/3. This is going to be what? This is going to be a 3/15. So it's going to be 225. So these exponents are going to get, because of the squaring of because this is the actual work being done. So when the work is linear, whatever you divide, that's your work. But if this is going to be n squared, then you're going to have to square that. So this would be n squared over 81, n squared over 225, n squared over 225, and then n squared over 625. Same problem. It's a realistic problem. It's the same problem, realistic problem, but just that the math is messier. So by keeping it the math this way, it was a little bit simpler. But do you understand why? Now,
Maybe the depth is
if the ratio was not less than 1 and it was going to infinity,
Yeah.
then this would go to infinity and we'd have no upper bound. So we'd have no way of knowing what the limit of the complexity was. Okay?
And if I wrote with that way, she talk about I can lose all points or
No, nobody's gonna lose all points. If you put in a good effort and you have some nice things that you're doing, then you'll get some points for sure, yeah. You don't have to worry about that. Right? Everybody's working hard in this class. Except for her, she's not working hard at all. Just kidding. All right, everybody's working hard, so you don't have to worry. Just as long as you're not leaving things blank. If you're leaving things blank, that's when I get worried. Or you're going into, or you're answering question 4 under question 1, and I get worried. I say, what was this person thinking? I get worried about that. But as long as you're answering and going towards the question, you know, you can make a small mistake. You know, it's not the end of the world as long as you're on the right thinking pattern. Okay? Any other questions? Okay, so we'll look at those on Wednesday. All right, so now we're going to switch gears. Yes, we are. So we are going to look at a probability type algorithm. And this probability type algorithm is going to be based on a scenario that I'm going to describe to you. In fact, we're going to look at 2 different problems that describe a similar scenario. The scenario is going to be, we're going to try to hire an assistant. It's very difficult to hire a good assistant, apparently. All right, so we're going to use an employment agency to hire a new office assistant. Okay? The agency will send us 1 person a day, so there's like 1 input per day. Now, we will interview the candidate, and we must immediately after the interview decide whether or not to hire the person. If we hire the person, we will immediately fire the current assistant. Okay? That's the model. Kind of cruel, but it's good for the person being hired, but it's bad for the person being fired. It's also bad for the person being hired in case we interview somebody better than them tomorrow. Then they will have to be fired. So you can see it's, the only person who could never be fired is who? The last person. The last person. They can only be hired or not hired, but they can't be fired. Why would we hire the last person? Why would we hire the last person? Why do we hire somebody? Let's say I'm interviewing you, but she's my assistant right now. Why do I want to hire you? No, you're better than her. So I'm interviewing you, but she's my assistant. And if you're better than her, I will hire you. But I only have 1 room for a payroll.